Hey there, this is Colin Ward with the Cougs and Space Club, and over here.
And I am Greg Wallace, also with Cougs and Space Club.
So today we're going to be going over for the current and future CubeSat or CubeSat members, Cougs and Space members, how to do random vibration analysis in Solidworks, as this is kind of the main test we need to do on our spacecraft from the hardware side of things. And obviously there's the actual physical random vibration test we can do. But as we're currently finding out, it's very hard to find equipment for a lot of this. So the current best thing we can do to test our model is to use SolidWorks random vibration simulation suite. So what we're going to do, as we have been researching this random vibration stuff for the last year, but we're not by no means experts, we're going to share with you what we've learned so far, some of the best practices we've found so far. But again, with the asterisk with all of this is, again, we're still learning as we do it. We're just documenting this for now so we can pass on the information we have so far. So you guys, if you find something different or something better we can do for this simulation approach, you guys can take it and run with it a different way. So yeah, without further ado, we are going to random vibe do a random vibe test using SolidWorks simulation of this current CubeSat Mark 8 or Mark II version 8 model. So yeah, I guess any other things that you want to add before we get started?
We removed the fasteners.
Oh, yeah, good. Thanks for reminding me. One other thing that, at least if you guys have access to this model and you're looking at it, is you'll notice there'll be fasteners that are all removed. The main reason we're removing all the fasteners is because for random vibration, though each of the fasteners, they will technically contribute a little bit of something to the model's movement. Because their mass is so small, the effect is very negligible. And it tends to make the simulation very long. So in this simulation case, we're opting to at least ignore their effects, and we're going to opt for doing bolt analysis and other tests to check to see if these guys will survive individually. So yeah, anything you add to that?
Yeah, so the...
Actually, you want to I'll slide this because you have to be more or less in the center of the screen. There you go.
Yeah, so the fasteners work by holding down pieces together. And we do not need that in this model because we are going to be using special contact bonds, and so the bolt wouldn't actually be doing anything anyways.
Cool. All right, so here's the first part. So setting up a random vibration simulation in SolidWorks. So the first thing you're going to do is you're going to go to the simulation tab. For a reason, this automatically pops up on my tab, but if you're not seeing it right away, go ahead and click to the SolidWorks add-ins, and you want to enable the SolidWorks simulation tab. So once you have that, for some older computers, it may take a little bit to load. You click on the simulation.
You should also be able to do that in the settings somewhere. I'm sure you can just find it online by Googling it. If you can't find the simulation tab.
Yeah, for a reason, and if you tried those two approaches, you still can't find it, talk to your team lead, because they might know, or talk to the SolidWorks instructor on campus. Or if you guys are on the internet and don't have access to that, I guess Google and forums are always helpful. So once you're on the simulation tab, you're going to go and create a new study. So you're going to click the arrow down below, hit new study. So we are doing random vibration, and it's a little bit cryptic actually how you find it. It honestly took a long amount of Googling and searching to find what exactly of all these different simulation types you would choose for random vibration. But the one you end up choosing is the linear dynamic. You click here, and you go down to random vibration. And that's the one you end up choosing, and we'll rename it. We'll just keep it dynamic 1 for now. And we'll hit OK. I'll give it a second to load, and voila, we are now in the dynamic 1 simulation part. So now that we're in the simulation part, we first have to set up our model to get it ready to simulate. And there are a few components that are involved in that, so we're going to walk you through that part to begin with. So the first part you're going to do, so for every part of the CubeSat, is you're going to make sure each part has a material type assigned to it. So if you open up parts and you're looking here, if you see a check mark next to it, you'll see that, okay, the material type does have, or the given object does have a material type selected to it, so you should be good to go. Down here, you're noticing these guys do not have material types, so you would have to go in, right-click, add material type to it. For this case, just for this tutorial, we're going to go ahead and actually shift left-click, and I'm going to suppress exclude from the analysis for now, just so we can get the tutorial going, but you would want to go back and find those if you deem that these were necessary for simulating. And another thing you'll want to do because this is something we also make a mistake a lot. So for some of the materials, you want to make sure all the material properties have been defined, so that whatever material, in our case, we're using E-glass fiber for this. That E-glass fiber currently has its modulus, or Young's modulus, and a bunch of other yield strength, and a bunch of other parameters attached to it. If SolidWorks does not crash.
You don't necessarily need every single one of them filled in, but some of them are going to be a lot more important than others. So obviously need density, Young's modulus, some more mechanical properties. But one of them is a damping coefficient.
Yeah.
I can't remember what that one's called in it. But that will be important if you want to do in the damping we do later.
Yeah.
So I believe it's at the bottom. Material damping. Let's call that.
Yeah.
Material damping ratio.
Yep,
Yeah.
right down here. Yeah. So one error we found when we were running SolidWorks simulations is that you'll start running the simulation and it says material properties not defined. So what that would mean, at least in our case, what we ended up finding was this E-glass fiber material that we're setting to all of our little PCB board analogs in here. They don't actually have all the necessary values for the program to do all the necessary calculations for it. So for whatever material you're using, make sure you get all these variables. In this case, I'm going to go ahead and I'm going to suppress most of these, and just so we can keep the tutorial flowing. Again, just make sure so suppress.
We will in the future want to test all of those together, but for now we don't have all the properties correctly known. And the reason that they're not in the SolidWorks is because it varies a lot by manufacturer or how that material is actually made. So if you have aluminum T, or aluminum 661 T6, then it's going to have some standard properties. But when it comes to fiberglass boards and stuff, they may not be very consistent, so they don't like to list those. So what we do is we're just gonna, or in the future, we're gonna go look at online, what are some standard numbers for it, and then we're just gonna go from there until we find something better. Because the manufacturers for the board don't actually give any material properties because they're not really designed to have material properties other than just hold together and be an insulator.
Yep. Yeah, so for things like the frame, for instance, like we're using aluminum, that stuff's pretty standard because, okay, this is all we made of aluminum. Like in our case, 6661. SolidWorks has a great library and it has all the variables, or the values for all the parameters, like dampening coefficient, Young's modulus preset. But yeah, like Greg was saying, if you have custom stuff like PCB boards and stuff like that, you're going to probably have to do some research about the material properties of that. So at least in this case, I'm going to keep one of them open, and I'm going to actually assign copper as its material just because we have no material properties for that. And we're going to try to reopen this.
Oh, another thing, when you do have your own properties that you put in, you're going to have to make it a custom material. And then you can call it whatever you want, and you just need to add them all, or add the properties manually. But yeah, in doing that, then you can actually use it because you can't change the built-in ones so far as I can tell.
Yeah, so adding custom material.
Something.
Remember how to do. You just
I believe.
Yeah, we don't have to set the
Yeah,
whole
so
process.
I believe you just take some alloy, or take some manganese bronze. Good enough. Let's see, copy, and then.
I'm going to go
Let's try to copy
and then
that.
paste it into plastic.
Oh yeah.
Paste. Yep,
Paste.
there you go.
Boom. And tin bearing. Whatever.
Yeah.
And then now you can change these. So I'm gonna just say fuck you and change.
Change it to 11. Wow.
Boom. All right. Apply. Boom.
So now you
Now we have a not at all accurate property, but it shows you how you can change it.
Yep.
We're not using that one, by the way. How are you finishing?
Yo. May have to pause it for now. Where were we? Okay, yeah, so that's how you do custom property, or yeah, if you want to make custom material, that's how you do it really quickly. Anyways, click this. So, all the parts have material property, or materials defined, they all have numbers in for them. Next thing we're going to do is we're going to do connections. So, each of these, as we're in the assembly view, there's going to be there's going to be a bunch of different parts that we all have to assemble together that you do in assembly. But now, some of you are familiar with SolidWorks assembly, you have different mates, so you can do eccentric, you can do like perpendicular, stuff like that.
Can we start with fixtures first?
You want to do fixtures?
Yeah.
And jump to that? Okay, yeah, we can do.
So, fixtures are basically an attachment sort of feature, but they specifically define where the input is going to be. So fixtures are going to be where the vibration is going to be induced in the model. So naturally, when you're shaking, the shaking is coming from somewhere else. So in our case, we're going to be applying a fixture to the feet, the bottom surface of the feet of the CubeSat.
Yeah,
That's where the load is going to be applied.
Yeah, and I guess to give you more context, the way we're determining that is, so the P-pod's going to be, or not the P-pod, the CubeSat is going to be sitting in a device called a P-pod, which is what this is going to be launched in. It's going to be sitting, the way it's going to be sitting in, it's going to be in contact with the P-pod at these points, and like at the top and the bottom. So we're going to create fixtures to model those connection points. So that way, because at least the P-pod's not going to contact like the bottom part of here at all, so you wouldn't want to put one in here. But again, because the P-pod's going to be contacting here, you're going to put a fixture point here because it's probably going to shake it from those spots. So we're going to create, at least at this point, we're just going to create it. I think for this tutorial, we're going to treat it like it's being connected at these top four corners here, these bottom four corners here. But again, you would probably check it against what you would need to have. You need to first. If you're using, like we do something else besides a P-pod, for instance, you would need to understand what other environment this is going to be sitting in. Is it going to be maybe mounted some other different way? And then you model that mounting, system accordingly.
Yeah, so we can, so we're just doing it on the tips of the feet right now. We could also model it so it's being applied to some of the surfaces of the rails. That would be a good thing to check. I don't think it'll make too much difference, but you could also do it that way.
Yep. So we'll go ahead and do that. So we're going to go right click. In this case, it's going to be fixed geometry. So we have to click that. Now we're going to select our faces. So as we said before, we're going to be choosing these corners up here. So we're going to go ahead and left click this guy. And we're just going to do it to the top of this accordingly. 4. Rotate. 5, 6, 7, 8. All right, so now we have our 8 points fixed. Fixed geometry, hit OK. And now we have our fixtures defined. So the next thing we're going to do, would external loads be the next part? Anything else you want to add to fixtures? Okay, so the next part we're going to go to is the external loads. This is the part where you define what forces your given structure is going to be experiencing. In our case, it's going to be, we're doing a random vibration, so it's going to be experiencing random vibration, basic excitation forces. So we're going to go ahead and define those in here. So we go ahead, we'll click external loads, right click on it, and we'll open uniform basic excitation. And now
it is where we define how it's going to be excited, basically.
Yeah.
And once again, this is at the fixture points on the legs.
Yep.
And so these two things are directly work with each other.
Yeah. So now that we have this selected, now we need to put in our input variables or input forces. These will be usually pulled out from your launch service provider. In our case, because we don't have a launch service provider yet, we're pulling it from a standard called the GEV 700 standard, which 7,000. There's an extra zero somewhere in there, which gives us the forces in acceleration. So we're going to go ahead and select. Okay, it's going to be uniform basic excitation acceleration. It's given in, because I've just done this so many times, I'm kind of sick of it. It's given in g squared over hertz, weird unit. And then they give us the input as a curve.
Also, we need to choose which
direction, yeah.
Which direction. So for now, we're just going to do normal. So that's going to be up and down.
Like
those
along,
fixture points.
Along the.
But it could also be. We could also do it sideways in either direction, and we will need to test all those ones. So
yep.
Just keep that in mind.
So when you say normal, you mean go up and down the z-axis?
Perpendicular to the surface. So you got these surfaces and they're flat. It's going to be going up and down, straight up and down.
Perfect. So we would, if we want to do normal, yes, normal to plane.
And set it to 1.
Yes.
Just if you wanted to double it, then you can set it to 2. The reason we're doing 1 is because we're going to use a curve.
Yes.
And we're going to show in that curve what the values are, and then it's going to multiply it by the number that we put in. So we want to multiply by 1 so it doesn't change.
Yep. So yeah, now that the grid goes saying, okay, now we have the direction that's being shaken in. I was talking to Dave, one of the guys who's a SolidWorks expert. You're gonna actually, once you do one axis, you'll actually have to go through, do this exact same step, and you'll do it along. Okay, you'll do this exact same step, but now along the other axis, and then you'll do it along the third axis, because I mean this is gonna experience vibrations in 3 different directions. In this case, we're just gonna set along the normal plane, or at least in this case, the Z-axis. So we're just going to select it here, select 1. But the process for all the other axes will be the same. Just make sure you switch to this parameter for the given simulation. So we're going to go in here, variation with frequency, we're going to hit edit. And now we're going to pull up numbers from the GEV standard. In this case, you're going to have to do a little bit determining what forces you're going to pull up. In our case, we're doing if I remember right, we're doing the qualification numbers, which is the heaviest forces it's going to experience on those spacecraft.
In the future, we will want to do the whatever the actual one will be tested at, but we don't know what that is yet.
Yep. So we're just choosing.
The reason we want to do that one is so that we can directly compare what the results we get are. Because if we make this test too conservative, then we won't really be able to compare them. So we want to make it as close to that as we can. But just for now, we're going over the top, just so we can over-define everything. Or we can make everything strong enough.
Yeah, and just make sure we have very significant margins of safety and stuff like that. So the first thing, actually pulling up the numbers from here, you'll want to look at, again, the GEV's 7,000 standard. For whatever reason you're not finding them, talk to your team lead, and they should be able to pull them up for you. In our case, the X variable is going to be in hertz, and the Y is NA, but in this case, this is going to be preset to the G squared over hertz. So for our first point, we're going to set this to 20, and that value is going to be 0.026. The second value is going to be 50, and then that value is going to be 0.16. And then this is where it gets a little bit confusing because SolidWorks has a very unintuitive interface for adding these curves. If you want to add a new point, you have to double-click on the number, and boom. Now you get another point. So we can add our third point, which is 800 at 0.16. And we're going to add our fourth point, which is at 2,000. And I think that, if I remember right, it's at 0.026. And so usually the frequencies are defined from 20 to 2,000 hertz, so that's where we input it in. But I think there's a reason you could explain why we put it in at 3,000, another 3,000 variable.
Yeah, so ultimately one of the sources we were reading suggested that we read data up to 150% of our max value, which would be 3,000 hertz. But we can't measure it in SolidWorks unless we also give it a frequent or an amplitude up to within the entire range of what we want to read. So basically, we need to add one final row of 3,000 and set that to 0. Now it will technically create a curve, as you can see in the slightly upper right here. So it will add a little bit of space between 2,000 and 3,000, and we're just going to ignore that. If you want to get really exact, you could make another step in between there at 2001 or something like that and set that at 0, so it drops off immediately, and it's 0 from there to 3,000. It shouldn't matter. This is already very low to begin with, so we're just going to go with that.
Yep, so now we have our numbers put in, everything looks great. Hit OK. So now we have our curve set, we have what direction we're putting in, we have it at 1. So now we have our uniform base excitation external load defined. Next thing we're going to do, actually, do you want to do connections or meshing?
Actually, let's set the simulation properties.
Okay, actually, how do you do that?
Yeah, so we want to be able to read within the range we gave, so 20 hertz to 3,000 hertz, or at least up to 2,000 hertz. SolidWorks requires you to input that in 2 different places because apparently it can't read from 2 different places. It can't just copy and paste it apparently. So to change what we're reading, we right click on dynamic, and then we go to properties, which is right here. We go to frequency options, which is what we're on. Don't care about that. Number of frequencies, don't care. Let me see.
Yeah, I think you want your automatic solver. So
automatic solver selection, yeah. So we want to have that on. That'll just help prevent some errors from being thrown. So if it tries to solve it one way, that it's just not going to work, and it might be able to tell that beforehand and switch to a different one. And then in the random vibration options, we are in cycles per second, which is hertz.
Yep.
So the lower bound, it's set at 0, which if we tried to run it right now, it would not work because we're trying to read data outside of what they gave us. So we need to actually input it again.
Yeah.
So
Actually,
20 to 3000 hertz.
one note on that, you'll see an error sometimes pop up that'll say like frequency parameters not defined or something like that. That usually means that you put in for your external lows option 20 to 30,000 hertz, but you forgot to define it about here. Made that mistake a few times, so if you do see that one, this is where you fix that.
The other common thing is not putting in the units for the what was it, the external loads.
Yeah.
So if you accidentally put it in something other than
Gigahertz or gravity squared.
Hertz or gravity squared per hertz.
Yeah.
Then it'll also give you those problems. So if you're coming up with a thing that's saying, something weird about the frequency bounds, and that's probably the cause.
Yep.
So.
Yeah, cool. So we have, let's see, now we have those properties set. I'm trying to think if there's any other things for that. Nope. Yes.
Damping.
Yeah, so we can do global dampening. This one, again, we still have a lot to figure out and explore. For now, actually, do you want to explain what the dampening ratio is, and then I guess how we came to our general guess about what we're putting in for this structure?
Yeah. So if a material doesn't have any damping, then hit it like a tuning fork, and it'll vibrate and vibrate and just vibrate forever. In real life, some of that energy goes into deforming the material, which produces heat. So that vibrational energy turns into heat slowly. And how fast it does that is basically damping. Not dampening, that's you get water on something, just to be clear. So damping, we're going to say it wrong, I'm sure, a couple times in this video. But so, what we're going to use is 1/40. So that is a very rough just guess for what the damping is. So what it would be ideal if we go back to that. What would be ideal is we would compute them from material damping. So that would be if we had all the materials in there correctly and they had damping values. But currently, basic aluminum doesn't have that. So we're just going to set a rough estimate of 1/40 because there's some math behind it, but that gives us a Q value of 20, which is just another vibration damping parameter. I don't remember what it's called, just Q.
I think it's like the resonance or whatever.
Yeah, something about resonance. It's also the guy in Star Trek. It was one of the guys in Star Trek. So,
okay.
I remember that because the day in Planetary that we were talking about it, they were running a Star Trek episode, and guess who was in it? Q. Yeah. So, anyways,
there you go,
we're
kids.
setting it at 1/40 for now. In the future, it'd be best if we had all the materials properly selected. And we could do it would just automatically select a value, so you don't have to put some in. We don't have it at that point yet. So for now, we're just going to do modal damping at 1/40.
Yeah, so is this a good default value to put in if you don't know?
I think it's okay, although I haven't had any verification on it, so kind of just guessing.
Gotcha.
So for now, we're just going to go with that. And,
Vaguely
we'll need to improve it later.
Vaguely trust, but definitely verify our dampening ratio number here. So yeah, we got dampening ratio in. So now we have two more parts we need to do. The next part is going to be the connections. So the connections is for you guys who are familiar with Solidworks assembly, you're familiar with the idea of mating, and mating is how you define where a part's position is relative, at least how the part's assembled together and everything like that. The mates in the simulation part, outside of, I guess, defining where a part's position is, that does not define how the part interacts with another part or how they are connected together. So the component contacts of the connections define how the parts are connected together. So if you have, like in our case, we have a bunch of bolts. Oh, actually, we have 2 more bolts here that we need to get rid of for our simulation, speaking of which. Let's get those really quick.
Yeah, so the all of the mates that you put in for the assembly, they're just going to get ignored. So just keep that in mind. You have to redefine how everything's attached.
Yep, and you do that, through the component contacts. In this case, do we just want to do, I think like a simple, if I remember, you can do a global contact, so everything's bonded to everything together. And then one thing you can do, if you just want to set up a simulation, make sure everything runs, you can click a non-touching faces option. So if there's any faces that are more or less contacting, but there's like a tiny little gap, if you set this and you set this to 1 millimeter, then this defines that, okay, if these parts are like within like a millimeter, they're pretty much touching. There's like something weird with how 0.1. Okay, 0.1 would be more conservative. But yeah, that just for a reason, if it's something in the assembly, something went wonky, and there's like a little gap, this makes sure that the parts will actually be touching each other, so you can set up the simulation.
So when we do the full-on one, we will need to go back and make sure all of the individual components are attached basically just correctly and as accurately as we can. So if you have 2 plates that are bolted together, they don't just act like they're welded together as a single piece. They act like they have small areas of contact where they're welded together, and that's just around the bolt. So as long as the bolt is doing its job, a small round area around it is acting like it's welded together or it's the same material.
Yeah.
So just make sure when you're adding those bonded contacts that you're only doing it for certain areas around where the fastener is.
Yeah, so like for instance, this, if we go to like this little connection point here, the way that this part and then this part interface is between this little bolt here. So you would put like a contact bond around this area versus what we have so far is we just have everything that's touching each other, that's bonded, everything's welded. This is not the most accurate setup, but this just allows us to continue the tutorial and just get everything set up and running. But again, you want to keep in mind how your parts are connecting together and then do the appropriate contacts around that. And actually, do you have any good resources outside of maybe talking to your Solidworks professor about how to set up those more granular or those more specific bonding methods?
The only thing I have is that when you try to do them, you can't select part of the surface. As far as I can tell, you have to do the whole surface, which isn't quite accurate. So in the model that you're making for it, consider trying to calculate what the actual area is going to be, and that's going to be in my bolt hole analysis sort of thing. It'll give you an area of contact around the bolt that acts as if it's one material. And so one option is just to make a teeny tiny
sketch
tube shape, teeny tiny cut into the material such that you can separate that material from the stuff around it, and that way you can attach just that face.
Gotcha. So if I did a little cut around here, so it becomes its own feature, then I could say, okay, this spot and then this face, they're connecting here.
Yeah. So if I hide this part real fast, it's going to be attaching around here in a circle. So maybe make a small cut in the shape of a circle around this, and then just fix this circular surface, this tube-shaped surface.
Yeah.
To the next one, and then do the same for the other side. So
and that'd be like the closest thing you could do.
Yeah, so that's about going to be the most accurate as we can get. You have to be careful to make sure you don't add. It's not going to cause any stress concentrations. But as long as you don't make it very deep, it's probably fine.
Gotcha. Okay. Yeah. So that again, this is another area where we're still looking to improve a lot on it. This is something we're just telling you guys what we know so far, and you guys will probably have to improve on this and maybe make your own tutorials about how to improve that part of the process. But now we have the contact part set up. And again, everything's kind of welded together. Not the most accurate. You probably want to get more granular again. And then, pause it. All right, so the final part, you have your parts with materials defined. You have your connections. In this case, non-accurate, but make sure they're accurate. Be a little bit more granular about that. You have your external loads. So that was pulled from like GEV 7000 or your launch service provider. They give you your numbers. Damping coefficient, again, more room for improvement there. The final thing you need to do is you need to create a mesh of the object. So actually, do you want to explain what meshing is?
So the way Solidworks and most programs figure out, basically calculate a solution for how something works is it makes a whole bunch of points in the structure, and then it assumes that it's connected to the ones around it linearly. So basically it's taking, making like a simple beam between each of the points that it's connected to, and then it's just doing that equation a bunch of times. They use matrices to solve it, and they can come up with some very good solutions compared to trying to make exact ones when you're trying to do complicated parts. So that's why they don't try to come up with perfectly accurate geometric solutions, because it would require a whole bunch of integration. It would just never run. But you can define how much space is between the points you take, between the different points. And smaller distance means it's going to be more accurate because you have more data points. And that would be a very fine mesh. But it also means it's going to take a lot longer.
Yeah.
Double the points, I imagine it roughly doubles the time. Maybe it might be squared time, I don't know.
Yeah.
But so having a finer mesh means it's going to take a lot more time. So we want to actually make, so finer mesh means it's going to be more accurate, but it's going to take a lot more time. A more coarse mesh means it's not going to be quite as accurate, but it's going to be faster. So for now, we're going to do a coarse mesh, just to make sure it runs.
Yeah.
And we suggest starting off with that just to make sure it runs, and then
make it finer and finer.
Make it finer later. Now you will need to go in and make sure manually that they look okay. So for example, if you have a hole and it might be a stress concentration, then you may want the mesh to be a lot finer around that. So that's a good thing to check. And that is something you can change in the parameters. You should be able to read up online about it quite a bit. But for now, we're going to ignore that at the same time.
Yeah, and one thing when you're meshing things, you start with as coarse as you can and go finer and finer. Sometimes it won't mesh properly, and at least I found, at least just with a little bit of experimenting around, sometimes I find solving the mesh problems, if you make a finer mesh, it seems to do, like if it has weird angles, if you have a finer mesh, that solves that okay. But yeah, if you can't start with a coarse option, another...
So coarse ones that may not be able to quite form the mesh properly, so you may need to make it a little more fine.
So we'll start in between, and if for a reason we can do it. Let's see, remesh, and one other thing Dave suggested, who's the SolidWorks professor here, another thing he suggested is you remesh failed parts with incompatible mesh. So basically, at least a little bit, I only have a vague understanding how this works. I think he does as well. But basically, it's going to try to create meshes when everything's contacted together, so it'll create the triangle between two parts. For whatever reason, when two parts are contacted, it can't create the triangle there. It'll actually just create the mesh for each part separately, so at least that way they can get some calculations. So yeah.
And it won't fail after 40 minutes, and then you have to totally restart it.
Yep, exactly. So we'll go ahead, we'll hit OK. It'll probably take a little bit to mesh. At least two bodies are interfering. Oh, that's one other thing we have to do. Yes. Okay. You have to also check for interference. So we will calculate. Okay, in this case, again, for SolidWorks simulation, if you're simulating parts and parts are interfering, it's, at least in the assembly part, it's not, the thing can't compute because, like, well, this body is inside this other body. What the fuck does that even mean? So in this case, because it looks like most, if not all, the interference, actually there's a lot of interference. Just press everything. All right, so we're back. We ended up troubleshooting the problem. I'm actually back in my apartment right now, but Greg has passed everything he wanted me to communicate for the rest of this tutorial to you. So the first thing, I guess, is to show you what was causing all the collision interference. So we have this volume limits, I guess, feature that we use a lot, at least for this CubeSat, just to show, at least that Greg made to show just where we could fit given components, because at least in addition to the 100 by 100 millimeter dimensions, we actually are allowed to have components stick out up to, I think, a 6.5 millimeters. So he created this little volume limits assembly just to show that. But we forgot to suppress it. So that's why we're having all these collision problems. So now that we suppress it and we run a interference detection, we actually only have a couple different problems. So we'll troubleshoot them one by one. The first one, I think, is coming from the spring itself. And the second one I know is because there's a threaded problem here. Yeah, so we'll sort those out one by one. This one, oh, actually, it's just because we left it boolean. So that's the first problem here. So that should sort that one out. And now if we do interference detection. All right, so it looks like there was actually a micro switch that was not popping up. I think that was invisible, so I ended up suppressing it. So now if we do interference detection, see no interferences, cool. Now we know we're good to go. So now if we go back to our dynamic random vibration study, just give it a quick check over, everything looking good. Go ahead and create mesh, and we'll start the process. Great, so now everything's meshed. Looks like I meshed pretty well, even at a slightly less fine setting. Just doing a quick inspection, everything's looking pretty good. Triangle's looking good. So we're going to go ahead and hit run this study, and we're going to let SolidWorks work its wonders. While we're doing this, a couple more final notes. The first thing is if you're creating a SolidWorks file, or if you're doing a SolidWorks simulation, make sure your file is actually physically on the computer, not just on a hard drive, or not a hard drive, but a flash drive. Here we go. Here's actually the first problem that we're running into. So modulus elasticity smaller than element number 1. So this tells me that there's actually a material in here, probably one of our custom ones, that is being problematic. So we're going to go ahead and change. So it fails, so we're going to go ahead and look. That's why. Okay, let's see, what material are these? I think these guys are glass fiber. And if we edit the material, now if we look at the material, oh, look at that. I think this is actually one we were talking about. This one doesn't have defined material properties. So obviously, when it's looking for elastic modulus, it's like, oh, it doesn't have a value for that. So we're going to go ahead. I'm going to go ahead and suppress these guys for now. I already remove them from the analysis. See, on the backplane assembly 2, I think it's going to be a similar deal. So we'll actually change that one to just copper for now. Again, we'll have to figure out what materials each of these are, and then make sure to put in the proper material properties for each of these. But now we should be good. Hopefully, I didn't just jinx myself. I'll make sure to save this. Now we're going to run the study once again, and we'll see how it, after it meshes everything, I'll go right back to normal. So again, like I was saying, for running simulations, make sure you're running it on the files that you're running are on your computer, not your flash drive, because as Greg was telling me when the video feed I ended up having cut out, he had done some simulation stuff on a flash drive in the CAD lab at our school, Washington State University, and there were some problems with that. So make sure if you're doing simulations, make sure your files are on your flash drive, but on your computer. So now we're going to let it run. I'll come back when it's done, and then I will point out to you guys what plots we're going to be looking for. Then once the simulation is done, what results and everything we're going to be looking at. Cool, so the simulation's done. Now we're going to go ahead and interpret the results. So the first thing I do is these results, as these will not be instantly. So the simulation's done. So let's go ahead and plot the results. So the first thing we're going to look at is the stress plot. We're going to go ahead, right-click, von Mises stress, newtons meter second. Yep, everything looks good. We'll hit OK. And this is what we're looking at. So the stress, or the von Mises stress, what this is going to be going over is going to, once you run your SolidWorks simulation, it's going to show you stress concentrations or force over area concentrations. So that way, if there are any high stress concentrations here, This would allow you to see, oh, okay, there seems like there's a hot spot around this area. Let me check to see if the given material, what its yield strength is, and if the stress here is passing this object's yield strength. Because if it is, there could be problems. Something may end up like, just at least end up stretching and then not compressing back into its original form. You may get some weird deformation and stuff like that. So this allows us to see what the hotspots are. Over here, it looks like we have a hotspot here. Von Mises stresses looks like it's about 2.4 to the E to negative 1. It's all color-coded nicely. Looks like it's around aluminum. So if I were to go and look at the yield strength of aluminum really quick. All right, so we have here the yield strength of aluminum pulled up on one of these engineering websites, and it looks like the yield strength of aluminum is 69 gigapascals, or 10 to the negative 9. If we go to, actually, this is Young's modulus. The yield strength of aluminum is 95 to the 10 to the negative 6. And it looks like around here, we're going to see no more than actually like 2.5 to the negative 1. So this model should be perfectly fine. As an additional safety factor, one thing people like to do is whatever number you're seeing here, multiply it by 3, and this gives you a 3 sigmas worth, let's call this 3 sigmas worth of, I guess, reliability. Or what that means is that, okay, if you take this number and you multiply it by 3, there's a 95% probability that the number will go higher, or that you'll get a yield strength higher than that. So it's just a little safety factor that you can factor in. But when we multiply this by 3, we're actually probably going to be, way orders of magnitude lower than the yield strength of aluminum. So yeah, this spot should be fine. Let's see if there's any other red spots we should be aware of. No, so yeah, overall, really well designed model so far. Again, this is assuming everything's welded to each other, so obviously we have to go back and make sure the contact points are accurate. But so far, so good. It's especially good to see the boards looking fine here. The next thing you're going to look at in your random vibration analysis is the displacement. So we're going to go in here, millimeters, that's a good amount. And here we're going to look at the hotspots. So right here, we can see obviously the board here is going to be the one that's going to be displaced the most, which is for CubeSats. This is going to be the main place we're worried about, because the reason we're looking at displacement is to make sure the boards, so the components on the boards, don't bump into each other. So in this case, it looks like the boards here should flex no more than 0.3 millimeters at their worst. If you wanted to add that 3 sigma of safety factor, you multiply 3 by 3. So I think, assuming worst case scenario, these boards should move no more than a millimeter inch, or not millimeter inch. Vibrate no more than a millimeter, or displace no more than a millimeter. So as long as you have your board spaced, the top component is spaced, like 2 millimeters away from the bottom of the board, assuming the board's moving down the millimeter and this part's moving up, there's a very, very unlikely probability that they'll hit each other. So yeah, this would be another thing you can look into to inform your design process. So yeah, there you go. That's the basics of random vibration in SolidWorks. Again, still a lot of room for improvement, but this at least shows you how to set up a basic setup in SolidWorks, how to do it in the context of doing CubeSats. So now, the things you need to tweak is, one, again, the dampening ratio. We're not sure if this is actually the right one to use. We just kind of guesstimated it a lot from the limited knowledge we have. 2, you have to improve your contact bonds because everything's not welded to each other again. I think that's pretty much it. Oh, and 3, you have to go to your parts. And you make sure you're setting the correct material properties, especially if you have things like PCB boards, and you might want to make sure you can get a good data sheet for that, so you can accurately model that in a simulation. So yeah, that's been it. This has been Colin Warren from Cougs in Space, and again, my partner Greg, who is not here because we have to record this later. Thanks again for watching. Hopefully this helps you guys out and within Cougs in Space, or even if there's not any Cougs in Space guys, if these are just people looking for SolidWorks simulations. Hopefully this short tutorial from what we know after a year of studying this is helpful. Yeah, until later, take care, and happy simulations to you all. Whatever the fuck that means.